Okay, so we know that speech is a voluntary motor act that requires our voluntary neurological system regulating motor movements to be intact in order to have voluntary movements occurring, to have good, quick, rapid, strong, coordinated movements in the respiratory, phonatory, resonance, articulation, and prosody systems in order to achieve speech. There are many different parts of the neurological system involved in motor movement for voluntary movements, and one high level conceptualization to think about all the different parts of the nervous system involved is to break it down into three stages: motor planning, motor programming, and motor execution for voluntary motor movements. Motor planning is the first conceptual level. It is higher order and goal oriented in terms of where muscles need to be moving in space. It's focused on what the movement goal is going to be in terms of speech. That's focused on articulatory accuracy. The motor plans, as they're originally conceptualized, are inflexible, and it's going to set the place and manner for articulation primarily. There are multiple areas of the cortex in the dominant hemisphere involved with motor planning, including the premotor cortex, supplementary motor cortex, insula, parietal lobe. And when we damage motor planning cortex areas, that's when we end up with apraxia of speech that disrupts the accuracy and speed of movements. Different disorders occur when we have damage to motor programming areas of the nervous system. In terms of motor programming, we're going to involve the basal ganglia control circuits and the cerebellar control circuits. Initial motor plans are going to be sent from motor planning cortex to the basal ganglia and cerebellum for further processing that's a little bit lower level. It's going to be more focused on the procedure of how to carry out these motions now, and these movements will be modifiable through sensory feedback. So motor programming through the basal ganglia and cerebellum is going to help refine that initial motor plan to help gauge the size of movement, set the background tone and posture for movements, and help to regulate which movements should or should not occur to achieve our motor plan. So the basal ganglia and cerebellum are involved there, and when we have damage to motor programming areas, this can lead to three different types of dysarthrias associated with motor programming disorders, including ataxic, hypokinetic, and hyperkinetic dysarthrias that do not affect muscle strength, but do disrupt muscle tone, accuracy of movements, range of motion, speed of movement, and steadiness of movements. Then our third conceptual level of voluntary motion is motor execution. Once we planned and programmed voluntary movements, those signals are then sent from the basal ganglia and the cerebellum through the thalamus and up to our motor neurons, upper motor neurons and lower motor neurons. This is the lowest level of voluntary movement control in the neurological system. It is more muscle oriented and focused on carrying out the signal that has already been planned and programmed. And once again, we can modify motor execution movements based on sensory feedback. And the goal here is really to excite muscle movement, involving two different systems, the upper motor neurons and lower motor neurons. When we damage upper and lower motor neurons, we can end up now with strength differences, differences in muscle tone, range of motion, and speed of motion, but we do not disrupt accuracy or steadiness. Damage to motor execution pathways can give us three different kinds of dysarthrias, including flaccid, spastic, and unilateral upper motor neuron dysarthria, also known as UUMN. So we begin with our motor planning cortex to set where we're going to move. That signal is sent to our motor programming circuits from the cortex to the subcortex, and then we're going to end up back at the cortex at the end. The basal ganglia and cerebellar control circuits help to set the size, the movements, and inhibit the other movements that we don't need. And then all of those signals are sent back to the cortex to our upper motor neurons, which includes a pyramidal and an extrapyramidal system, to excite movements and help to regulate muscle tone and reflexes. And then from upper motor neurons down to lower motor neurons, which are in the peripheral nervous system, including cranial nerves and spinal nerves, to actually execute and carry out those signals down to the muscles. So 3 broad areas: planning, programming, and execution, involving different parts of the nervous system, with planning cortex, programming circuits, and motor neurons. One other visual depiction of this process: it is not a fully linear process. It is modifiable in some aspects by sensory feedback. So what you're seeing here is Don Fried's model from the original, his first edition textbook, with additions from Joe Duffy's textbook on a full model of conceptualization, from cognitive conceptualization, having a thought that you want to express, to a cognitive initiation, desire to move. Once we have that thought and the cognitive desire to move, we need to send those thoughts to linguistic areas in order to have linguistic planning, to choose the word, the morphemes, the correct phonology, to put those thoughts into words. And that is all cognitive and language based. And then from there we move into an elaborated model of speech production. So once we have the desire, we have a linguistic code, we need to translate that into a motor act. So motor planning is going to start with our motor planning association cortex, send the signals down simultaneously to the basal ganglia and the cerebellum for motor programming. Basal ganglia and cerebellum do their job for programming. They both output their signal to the thalamus. Thalamus then sends the signal up to upper motor neurons, the primary motor cortex, including a pyramidal and an extrapyramidal system of the upper motor neurons. Upper motor neurons send their signal to the lower motor neurons, which are the cranial or spinal nerves, and those are the peripheral nerves that carry the signal out to the muscles in the body. Acetylcholine is delivered at the neuromuscular junction from a nerve to a muscle to tell those muscles to contract, and we get an acoustic speech product that is hopefully intelligible. And if we have good auditory feedback, we also get sensory feedback that we can use to modify our motor programs and motor execution. If we are not being loud enough or not being clear enough, we can work on exaggerating that based on feedback. That's our model of speech production, and as we go through this course, we'll be focusing in on each one of these areas and the associated dysarthria for hypokinetic, hyperkinetic, ataxic, spastic, unilateral upper motor neuron, and flaccid dysarthrias associated with damage to each part of the nervous system, each one giving unique characteristics.